So this is section 1.4 where we start to deal with complex and imaginary numbers. The complex number is any number that can be represented in the form a plus bi. Notice the I, that's going to be for our imaginary piece, where a and b are real numbers and I is the imaginary unit that satisfies the equation I squared equals -1. In other words, I is the square root of -1, which we already knew, and remind ourselves that if we squared both sides, the square cancels the square root, and I squared would equal -1. So these are two definitions down here that we really just need to have with us at all times. Kind of think about them in terms of how we could use that information, okay? All right, we come down here, complex system. We're going to talk about the real piece and the imaginary piece. And in a standard form, we're going to have them separated like this, okay? And so just to kind of break down a little further, we have what's called a complex number. Now, complex numbers include real and imaginary. They kind of have to have both. When we talk about imaginary numbers, the real emphasis is on just the imaginary piece of the complex number. So the real piece should always be 0. So you're going to hear those terms used almost interchangeably, and you just want to make sure you're aware that, hey, there's the imaginary, there's the real, and when you put them together, you get the complex. So every real number can be written as a complex number like this, but we don't usually write 0i, just like we would put a 0 in front of 2i. So a complex number, we're typically referring to the real and imaginary put together. Now, there are a ton of applications, and these are just some of the implications or applications for complex numbers and the study of those numbers. It is so universally used to solve seriously meaningful problems like the electricity in your walls and the lots of different electricity and electromagnetic wave patterns. There's so much going on, as well as these pipes. It talks about fluids moving around pipes or trees. If you wanted to talk about a windbreak and you had several trees, as you have the wind come blowing past them, as they go around the trees, the problem becomes so complicated and so complex that we might need to use things like imaginary values in order to model the flow of the air. Because if you put too many trees close together, you can cause different problems. And if you spread them out too far, well, they don't create a good windbreak. So there is actually a placement between the trees that you would want to produce. It's very specific. So these are really interesting things that we could study. We're going to focus on just basic skills with them today. And so we're going to start with things like addition, subtraction, multiplication, and division. And this is just basic combine-like terms, if you will. The negative is going to distribute. To rewrite this problem as 2 plus 6i minus 12 plus 4i. If I combine my like terms, I'm going to get -10. And then I'm going to get plus 10i. We always write the real piece and then the imaginary piece. Here's we look at the next question. It's multiplication. Well, 5 times 6 is 30. 5 times -7i would be -35i. 4i times 6 would be plus 24i. And 4i times -7i would be -28. And this is important. It's I squared. The reason this matters is if we go back to our first slide, we said that whenever we saw I squared, it was equal to -1. So back to this question, we have this I squared. That means that this is really times -1. So a -1 times -28 makes this plus 28. And there's no I with that 28 anymore. So 30 and 28 is 58. A -35, a positive 24 is -9i. And there's our final answer for that. Actually, maybe that's -11. Back up the train. Mental math mistake. We're going to say it is -11i. Yeah, we all make mistakes. All right, we move on. Complex conjugates. When we multiply complex numbers, it is possible to get the complexity to go away. Specifically, when we multiply a complex number by its conjugate, where the sign has been switched. If you look at the math that happens here, you get a negative ABI and a positive ABI, and they're going to cancel each other out right down here. And that leaves us with, because of the I squared becoming negative 1, A squared plus B squared. So if you ever wondered, hey, does x squared plus 4 factor? The answer is x squared plus 4 doesn't factor unless you use imaginary values. So this is a little bit of a sidestep, but x plus 2i and x minus 2i would FOIL to produce x squared plus 4. We always had difference of squares. Now sum of squares can be factored, but only using imaginary numbers. And that's something we don't typically do. All right, so down here we've got 4 minus 6i, and we want to multiply by its conjugate. Well, if I remember right, everything's the same except the sign in the middle. And so now I need to multiply. That's going to be 16, be 24i, but then I minus 24i, and then I minus 36i squared. Now the I squared, remember, changes this guy's sign. So because 36 was negative, it becomes positive, because the I squared was a negative 1. All right, so now if I combine like terms, I'm going to get 36 and 16 is 52, but the 24i and the negative 24i changed. So the answer is just 52. There's no longer an imaginary problem. You might ask, is there a shortcut? If these always cancel, is there a shortcut? There is, but I want to be very careful about this. Look back up here. The answer turns out to be a squared plus b squared. If I look at the original problem, say it's 3 plus 2i, 3 squared, a squared, would be 9 plus, I totally ignore the I, ignore it. 2 squared is 4. If I multiplied 3 plus 2i times 3 minus 2i, I would have gotten 13. Now, there is a shortcut here, but you've got to make sure you set up the conjugate correctly. If you don't, it doesn't work. Let's look at an example that's done for us, where we're doing something more complicated. So this is actually a division problem right here. Well, we can't physically divide by imaginary values. It's not defined as a mathematical operation, so there's no set of rules we can use for division. However, our biggest goal is to get the I out of the denominator. And in order to do that, what we're going to do is we're going to multiply it by its complex conjugate, which is this 4 plus 5i. Now, on the bottom, 4 times 4 is 16. 5 squared is 25. If you look, because of that negative, this eventually becomes 16 plus 25 to give us the 49. On top, we go through the FOIL process. 8 plus 5i plus 12i plus 15i squared. Okay? And then the I squared is going to change it to a negative 15. And the negative 15 and the 8 becomes the negative 7. Now we always put the real, then the imaginary. Because we're in a college course, what we want to do is we want to break this down into what we call standard form. There's the real part, and there's the imaginary part. We want to keep them separated. Now one thing to keep in mind as we split this into two fractions, if one of the two fractions reduces, it's actually common practice to reduce. So this 7 over 49 is actually negative 1 over 7 plus 22 over 49, and they like to put the I at the back like it's a variable. Okay, so kind of keep that in mind as you solve these questions. Let's do this one on our own. So if you need to take a second, pause it and try it on your own. I'm going to go ahead and go through the process with you. The complex conjugate of the denominator would be 2 plus 5i. So I'm going to multiply top and bottom by 2 plus 5i. Becomes 14 plus 35i. And I've got 8i, so plus 8i. and plus 20i squared. Okay, all over. If I go through the whole process, I'm going to get a 4, a 10i, a negative 10i, and a negative 25i squared. But I also know that I squared changes the sign because it's a negative 1. So this is now a negative 20 up top. So if I combine my like terms, real numbers together, imaginary numbers together, on top 14 minus 20 is negative 6, plus 35 plus 8 is 43i. That's all over. The 10 and the negative 10 cancel. I have 4 plus 25, which would be 29. Now, if I finish this off, I'm going to get negative 6 over 29 plus 43 over 29i. That's its standard form answer. This is not too shabby right here. I take it 90% of the time, but I know any multiple choice tests and then maybe the final, it's really going to be emphasized that we get it into standard form. Well, just to make sure we understand this, we're going to use the same rules that we used for square roots before, except that when we break this down, typically what we're going to do is the square root of negative 1, square root of 5. And now we can break these down independently. This square root of negative 1 is going to be an I, and 5 doesn't break down, so I'll leave it as root 5. So essentially, every time you see a negative, you're going to pull an I out. If I look at this next example, there's a little bit more work here. Okay, this is obviously negative 1 times the root of 27, which is 3 and 9, which is 3 and 3. Like we did before, I've got 2 3's. That's going to come out. But remember, here, this square root of negative 1 also comes out, but it's represented by the letter I. And then I have the square root of anything that was left. It looks like there was a leftover 3. And now when I come to do the 48, it's square root of negative 1 times the square root of 48. And we want to break the 48 down. That'll be 2 and 24, 2 and 12, 2 and 6, 2 and 3. So I've got 2 2's there, and I've got 2 2's there. So that means I'm going to pull, there's a plus sign here. I'm going to pull a 2 times another 2 times, don't forget this guy, it's I. Root, was there anything left? Yeah, there was a 3 left over. So if I try to clean this up, this is 3i root 3 plus 2 times 2 is 4, 4i root 3 for a total of 7i root 3. Try not to let that get complicated when you're doing that problem. All right, well, that's it, and hopefully that's enough to kind of get you going. I'll see you in class.